All right, good morning, everyone. Sorry, I'm just getting my chair adjusted. Okay. So, usual due dates up to and including what we've done so far. We said that we are giving you a slight extension on the 5.1 homework because of the midterm. That's starting, what, tomorrow, right? Make sure you're always reading the next 1 to 2 sections. I do have your next Excel assignment listed now, and this should be, in terms of what you've seen for chapters 1 through 4, this should be the next one that you saw. I think we didn't do any from chapter 3. There's one I really like in chapter 3, but unfortunately it's whoever set the file up didn't really think about it. So there's something about the assignment that doesn't work properly, so we don't do it. It doesn't matter. But this is going to be the next one. And you'll notice I have 4-2 and then in parentheses 4-1. That is because of how it's laid out. I closed my math lab, so never mind, I'm not going to show it to you. But again, you don't see any other Excel files for chapter 4 before this one. That's the first one for chapter 4, and you can't miss it. It says budget in it. So that's going to be due on the 16th, which is a week from Thursday's class. Then our project is due on the 21st. The discussion board, I'm just going to keep this for now, the midterm discussion board. I might do an extra one today. I don't expect it. I kind of thought about it, but I think I'm just going to keep the phrase being drag y'all by the nose with it because the midterm's coming up. Again, taking a pause on the quizzes. We will do another quiz immediately after the midterm is done. We need to do a couple more of those to kind of even things out. Your midterm dates, nothing's changed there. It will be available as of 12:01 a.m. tomorrow, so less than 24 hours from now. You'll have 3 full 24-hour periods to complete it. Once it's the midnight of July 11th, that test will be shut down. You will not be allowed any other opportunities to take the midterm. And remember, there is a study guide for it. It's like 55, 60 questions. One of them I said to skip, like 43 part B, something like that. There is a formula sheet that's provided for you. This is in Canvas. So it's in that same section where it's midterm reviews, midterm whatever in Canvas. There should only be 2 or maybe 3 files that you see. There should be 1 for the questions, 1 for the formula sheet, and 1 for just kind of a general topic review, which is honestly just kind of taking the chapter 1 through 4 notes to share and condensing that down quite a bit. Remember I said you do have to know your time conversions, minutes to seconds to hours to days to years, but you don't need to know any other conversion formulas. You do need to know all those percent formulas, percent change, whether it's total change or percent change. You've got to know how to handle proportions. You've got to know how to handle proportions if it's a fraction equal a fraction, or y equals kx, or inversely proportional. We had those little subtle differences. But again, the review is pretty comparable to what will be on the test. I just trim the fat, so to say. There might be 1 or 2 Excel questions on the review, which means there might be 1 or 2 on the test. And by might, you can probably guess what word I should really be saying there. Hint, wink, nudge. I don't want to say too much, though. But yeah, I don't want to spend too much time just constantly going over this. We've been talking about it leading up to it, so you should be prepared. Remember, you do get 2 hours for each attempt, and I take your best attempt at 2 attempts. Yeah, all right, so let's get into new material. Excuse me. 5.2. So 5.1, we related equations of lines to the concept of proportionality, and we said, wow, with direct proportions, if you double one, the other doubles. That's not necessarily true with an equation of a line. And we said it is true if there's no constant in there, when there wasn't that fixed value or initial value. If it was just a variable amount, then we said, oh yeah, it is proportional. But with the extra fixed value like that, extra $20, excuse me, for the cell phone plan per month, no matter how many minutes you talk, or the extra 100 miles you already drove, no matter what your speed is, we said those just shifted the graph up vertically, basically. So instead of cutting through the origin, instead of having a 0, 0, it shifts it up. But we said, while you can't say with all lines if you double one, the other doubles, you can say if you double the change in one, the change in the other should also double. And we're going to start getting into that idea a little bit more in 5.2. So as a reminder, all equations of lines can be written as the sum of a fixed amount and a variable amount. Variable amount here, fixed amount. Fixed amount's just a number. Variable amount has a number and a variable. How do you know what number goes where? Well, the variable amount relates to the rate, the ratio, the miles per hour, the liters per gallon, things like that. The fixed amount is just a constant addition or an initial amount depending on the context. All right. So 5.2. Slope and Y-intercepts. Slope and Y-intercepts have everything to do with the A and the B in this equation above. They have everything to do with this A and this B. Slope is a measure of a steepness of a line. Slope is the measure of the steepness of a line. So back when we were doing when we were graphing those lines, and we said, all right, we got this line right here. I'll do it in black. And every time we went right, maybe this value is 5, we go up 1 to get to this point. That is consistent. If you keep going right 5 and up 1, you'll be on the line. If you go right 5 and up 1, you'll be on the line. So from this point, right 5 and then up 1. I'll put the 5 on the top this time. Right 5, up 1. So the slope is the ratio meaning fraction, of these numbers. It's always consistent. It's always constant. Now this 1 and the 5 in this random example here, we call these, sorry, my throat is really scratchy this morning apparently. We call these the rise and the run. So the 5 in this instance is what we would call the run, and it's not always a 5. And the 1 in this instance is what we would call the rise, and again, it's not always a 1. And we always think about ourselves going right. We're going right 5, and then you'd either go up or down. And we're going to get into more of those details soon. So that's how slope relates to a line. It's the ratio of how far you go right and then up or down, and then that just keeps being consistent for the rest of the line. If it was a curve, that would not be consistent. But we don't deal with curves in here for another chapter or so. Slope, again, relates to the A seen above. This number right here always ends up being the slope if you're solved for the Y. So just kind of a memo, it's the A above. And we'll see this all kind of come together. All right. The Y-intercept, which I already mentioned, is the B above, and I'll make that memo in addition soon, but the Y-intercept can be interpreted as a starting value or an initial value. And we said previously that your fixed amount can often be thought of as an initial amount. I said often, I said sometimes, I didn't say every time. I did not say every time, I did not say every time. I said sometimes or often or frequently, a quantifier. So Y-intercepts can be interpreted as a starting value, but for some applications, it's not always going to make sense. This is an important issue that we will study for the next, couple of classes here and there. For applications, specifically when we're talking about modeling using data, for applications, this value does not always make sense. And it has to do with our time scale more often than not. If we're looking on the short term, the starting value usually makes sense, but if we're looking on a long term, it often doesn't make sense. And we're going to study that moving forward, but I just want to kind of preemptively say that. And it doesn't have to be that those two statements are true. It doesn't have to be. In the long term, it cannot make sense. In the short term, it can make sense. All right, so slope. Let's go back to the idea of slope. And by the way, I meant to do this up here. Let's say this height right here on the graph, let's say this height was 12. That right there would be the y-intercept. This 12 right here, which is the height on the y-axis where you cross it, that's the interpretation of the y-intercept. And again, based on that y equals ax plus b, that's the b that's above. So this right here, this y equals ax plus b, and this doesn't have to be an a and a b, they can be any letters representing anything. But what I'm saying is the constant, the thing without a variable, that's what the y-intercept relates to. So y-intercept is kind of like your starting value. It's the initial height. Your slope is this ratio between the 2 points. So this is just a general way of denoting 2 points, these little sub-notations, sub-indexes, if you will. So when we say x1, y1, we're talking about the first point. When we say x2, y2, we're talking about the second point. These can also be abbreviated P1 for point 1 and P2 for point 2. So this kind of idea we have above, let's do this again, but more generalized with this x1, y1, x2, y2. Oops, wrong color. And I'm just going to keep this mostly in the upper right quadrant. So let's say, I don't want to make it look exactly the same as last time. Let's say this. Yeah, I don't want to have to do that either. Let's make it steeper. You know what? I lied. I'm going to make it very similar to the last one. So let's say here's our first point, P1, and here's our second point, P2. So P1 has coordinates of x1, comma y1. So this point would be x1, comma y1. And then this point would be x2, comma y2. It always goes x, comma y. Coordinates always go x, comma y. If you're getting them backwards, alphabetical order. That should solve your problem, I'd hope. They go in alphabetical order, x, comma y. So let's see what we got here. Slope is the rate of change between 2 points. The word rate, this word right here, rate, we have taught you as quantitative reasoning students that that word means fraction. And the word change, as quantitative reasoning students, we have taught you means difference. Now you might say, well, hold on, Mr. Beckner, we had total change and percent change. Total change was the difference, percent change was the ratio relative to the original. Okay, yes, when you say percent change, it has that extra little pizzazz to it. When we just say the word change, we're relating this to a total change idea, so this is just a difference. So slope is the fraction of changes, the fraction of differences between the 2 points. So if you just think about the horizontal distance right here, that distance, let's pretend that the x1 for just a hot second was a 1 and the x2 was a 10. So this distance right over here is 10, and then this distance right here is a 1. This horizontal length, and I know that's drawn a little poorly, but ignore it. I'm going to erase that stuff in a second. This horizontal length would have to be 9. Why? Because we started at 1 and we ended at 10. We went from 1 to 10. That means we increased by 9. Well, that turns out to be the differences of the x values. It's x2 minus x1. It's 10 minus 1, x2 minus x1. That's the difference of the x coordinates. Conversely, if you do that for the y's, this vertical distance, if you said maybe this height here was, I don't know, 8, and this height here was 6, this distance would have to be a 2, because 8 minus 6 is 2. If we started at 6 and we ended at 8, we went up 2. That's the change between the y values. So our slope formula, our M, is the ratio of the changes. Now again, the blue and the orange numbers, these are just made up to give you a better idea, but it's the ratio, so fraction of changes. We have to have a change in the y values divided by the change in the x values. These are subtraction symbols. We do the y's over the x's because some mathematician a long time ago said it makes more sense to study at y over x instead of x over y. When you see how it works numerically, it makes more sense. But some mathematician 1,000 years ago or 500 years ago could have said, let's do the x's over the y's. And we might think it makes a little less sense in our world, but if we grew up in that world, then, you know, it might make a little more sense to do things that way. But trust me, for us, it doesn't. So that's why we do y's over x's. So the change of the y's, we always do the future one minus the past one, or the new minus the old. 2 is new, 1 is old. And then over the x's, the new x value minus the old x value. See, this formula doesn't have to be memorized if you remember it as a concept as the rate of change or a fraction of differences. And I do have that formula written right here, typed up nicely. It's the same thing as what we just developed, though. It was the 9 divided by the 2 in this example. So for this example, and I'll use the colors, I'm sorry, I said 9 over 2. That was incorrect. It's 2 over 9. It's the change of the y's, which is this distance. It's the 2. And then over the change in the x's, which it moved 9 to the right. So 2 9ths. So again, that was just for the numbers we put in there. I said I was going to erase some things, but I decided not to. It's a little nicer keeping it there. You have to memorize this formula, or you have to memorize the concept. This is not a complex formula. It's a fraction of subtractions. It's fraction, subtraction, subtraction, fraction. Say that 5 times fast. But this is not a formula any math class should ever give you. I would never give you this formula in any of my math classes. I can't speak for every teacher in every class in the world, but I would never give any math student this formula. If you were on the scientific track, if you were going to go through the equivalent of Algebra 1 and Algebra 2, and then pre-calculus and calculus instead of this quantitative reasoning stuff, this formula never goes away. They have to continue to memorize it in pre-calc. They have to continue to memorize it in calculus. They have to continue to memorize it for all the rest of their mathematical classes of their careers. This is a very, very important formula. So also known as rise over run. Another way to say this, y2 minus y1 over x2 minus x1, or the rate of changes, is it's the rise over the run. I used those words earlier. We said that in this example, the 5 was the run and the 1 was the rise. The run is how far left or right you go. The rise is how far up or down you go. Now please note that rise can be negative. You're always moving right. The run is always how far right you move. The word left is not used anywhere. Do not ever consider yourself moving left. There is no left. There is no left. When you're talking about change, we're always moving forward in time, and on a graph, moving forward in time is typically moving right. Now, yes, not all graphs have to do with time, but we still just want to continue that concept even if we aren't talking about time. There is no left. So the run is how far you move right. The bottom number is how far you move right because that's the change in the horizontal positions. The rise is how far up or down you move, and that's the top number because that's the change of the heights. Y is the heights. So the rise is how far up or down you move. Up if it's positive, down if it's negative. So if your slope is positive, you'll get a line that looks like this. And I'm going back into just more general math, having all 4 quadrants. This would have a positive slope, m greater than 0, because you're moving right and up, right and up. Let me do that with a different color. Sorry there. Right and up. And your slope would be negative if your line looked more like this. If as you're moving right, you go down. So this would be a negative slope. You can also have zero slope. I'll put that in the middle here because 0 is between positive and negative values. A zero slope ends up looking like this. As you move right, I'm just putting this arrow a little higher because if I do it on the graph, it looks a little funny. I don't know, I guess that's okay since it's a different color. But as you move right, you don't move up or down at all. So this would be an m equals 0 case. It is possible to have a slope of 0. If the slope is 0, that means that the equation is constant. The output is always the same no matter what. So maybe you have a product that no matter what, you just always sell 100 of this product, no matter whether you make 1,000 of them, whether you make 10,000 of them, whether you charge $1, whether you charge $1 million, you always end up selling 100 of them because maybe there's 100 people that just have to have it. They have to have it to live, and that's never going to change. So if there's no change, it's a flat horizontal line. But when your lines do change, when there is change, when there's a cause and effects, you could be a positive slope or it could be negative slope. And again, in the real world, when we talk about modeling something, they don't have to be lines. And when we look at bigger pictures, they generally aren't lines. They tend to be curves, but we're building up to the curve concept. So that's our slopes. I'm thinking if I want to go into the Y-intercept stuff yet. No, let's go ahead and get to our guided worksheets. Oh, I didn't open this up. Oh no. All right, I'm gonna need a few minutes. I opened my math lab to open this earlier and then I got sidetracked and then I didn't. That's okay. This doesn't take too long. Nope, e-text. So we did these last time and these. Now, Excel preview, it says 4.1, this is actually 5.1, that's a typo. We will be doing this one, this might be our next assignment. I'm gonna say this might be our next assignment. Remember, every single Excel has an Excel preview in your guided worksheets. If you ever get stuck on something, this can be very helpful. So here's one. In particular with this assignment, I can tell you this. A lot of people mess up this graph. A lot of people end up having an extra line or 2 extra lines or maybe 1 less line than they're supposed to. I don't want to say which it is. I'm just telling you that the number of lines that people have tends to be off. And this shows you what it should look like. So if your graph doesn't look like this, you know, maybe figure out what's going on with that before you submit it and lose one of your attempts. All right, so here we are in 5.2. Slope and Y-intercepts. This statement right here, this is going to be used very, very, very frequently coming up. We're going to use it over and over and over and over and over. When we interpret slope, this is the quantitative reasoning sentence that's just cookie cutter. And I say cookie cutter in that it tells you to say the thing is changing by number units per units. And this seems very obtuse at first. And the first 1 or 2 times I ask you to use it in a sentence, everyone just stares at their paper and doesn't even pick up their pen. And it's really easy after you see it done once or twice. When we say the output, so every time there's these little sideways arrows, that's where we're going to insert either a number or a word or a unit based on what it says. So the output, for a lot of things, this would be the cost. So in the example above, the blah, blah, blah track phone with 5 cents per minute and a $20 fixed cost, which they don't even mention that part here. We said that the 5 cents related to the slope. Now, our output, the thing that we were getting, we were taking a number of minutes and finding a cost. So the output's a cost. So that's why when they say the output, they have the word the cost, because that's what we were finding, what type of measurement we were trying to find. The input, the thing we knew would be the number of minutes we talk. The output, the thing we had to deduce, is the cost. So the output or the cost. Then the words is changing by. Now this right here, there are some interchangeable words. You can also say is increasing, not increase in, increasing / decreasing. You only say one or the other. If you want to be more specific about the change, you could say the cost is increasing 5 cents per minute or $5.05 per minute. Or if this was dropping, then you could say the cost is decreasing by 5 cents per minute or $5 per minute, $0.05 per minute, excuse me. So these words are just more specific as to whether it's going up or down. If you don't use these words, if it's decreasing, you have to make the number negative though. So, is changing by could be replaced with increasing or decreasing, one or the other. By. Slope, this is just the number. The 5 cents per minute, this was the rate. So this is the slope. It's a rate, it's a slope. The Y units are the units of the output. These are the units of the output. It's a cost, so that's why we said dollars, or we could have said cents if we changed that to a 5 as the whole number. And then per X units. X units are the units of the input, which were minutes, because that's what we're basing off of everything in. So this is what goes in, this is what comes out in terms of units. The word per tells us it's a rate, and that's what slope is, it's a rate. So the output, which is very often price, not always, often, is changing by, then you write the number for your slope, and then you write a ratio of those two types of units, the output units to the input units. So we're going to practice making this sentence several times, and if there wasn't a midterm coming up, I would have this be a guided worksheet activity, but we're just going to do these together, again, in the interest of probably your sanity. All right, so to scroll. Please make sure you wrote that down somewhere, because you see it here, but you're not going to see it on the rest of them as we go through. Okay, so write that down, write it down 50 times, however many times you have to until you have that version of it memorized. Now, in terms of testing, I generally don't really throw sentence-based questions at you for a test. There could be a drop-down menu for this, that's a possibility. But if this was sentence-based, I wouldn't really care if you had this in an improper order or a very different format, as long as the sentence still made sense, as long as the sentence was still accurate. But if you do have a homework question on this, it's going to be typically done as a drop-down menu or an A, B, C, D selection. So you do have to make sure you understand this. All right, so first one. Monthly cell phone bill plan. Geez, we've seen this before. In fact, we were literally just talking about this one, but we're going to do it anyways. We have our Y equals 0.05x plus $20. So in terms of what these things meant, this 0.05, this was the rate of 5 cents per minute. That's what this was. And this 20, that was the fixed or initial cost, being 20 bucks. They want us to interpret the slope of the equation in real world terms. Interpret the slope. They did not say anything about the Y-intercept. Spoilers, the 20 is the Y-intercept. So we're not going to say anything about the 20. We're just talking about the slope, which is this 0.05. So we're going to use this sentence above quite literally. So let me put it on text so this can be nice and clean. Here we go. So cookie cutter, the output. So that's supposed to be the output, which is a what It's a cost. What is the thing we are talking about finding? We're trying to find a cost. You could be more specific. You could say the cost of the 5-cent plan with monthly fee, but let's just use one word, the cost. Then is changing by. So we use those words. Is, I'll be even more specific since that's a positive 0.05. I'll say is increasing by. I could say is changing by. Then this says slope. Use your eyes, pay attention. How do I know what to put? I'm just going straight from left to right on this sentence. Is changing by, then write the number for the slope, which is 0.05. Then the Y units, that's the output unit. The output units are in dollars. It even says it on the graph. Now, if you were building this, then it wouldn't say that. You'd have to know that. We're talking about a cost. Cost is in dollars. Again, I could also say 5 cents instead of $0.05. That would still be accurate. So the slope was the 0.05, the Y units was the dollars, then we have the word per, and then per X units. What was our input in? Well, our input was a number of minutes on the phone. So per minute. And you could, again, be more specific, per minute on the phone. There's lots of different ways you can phrase this. This is just the most condensed version of what we can say. Now, once again, I need you to be careful. Let's say this 0.05 was negative. For some reason, they're paying us 5 cents every minute. So that would say the cost is decreasing by 0.05. I wouldn't say negative 0.05 if I use the word decreasing. If I use the word changing, though, I'd have to say it's changing by negative 0.05. So the words are very specific. If you use the word changing, you'll need a negative in there. If you use the word decreasing, you don't want to put the negative in there because that would actually be a double negative, which is not right. Not right, actually. That's a triple negative to get the sentence right. That's it. That's all we're doing for these, I think, 4 problems. But I do need to erase this so I can move on. Not eraser, clear the screen. Let's see if I can get both of these on the screen at the same time. No, it's okay. It's better just to do it this way. Concentration of pollutants. So here we have a mathematical model, an equation with its graph. A model is an equation or a graph or both. We have the equation and the graph. So both of these are the model. They all relate to each other. If I say model, you can give me an equation. If I say model, you can give me a line. If I say model, you can give me both. This graph, this picture, represents this equation. So this right here is the concentration of pollutants in ppm. That stands for parts per million. So in other words, if you had 1 million particles of, say, water, parts per million would be the number of non-water particles in there. So if you had 1 part per million, that says that out of the 1 million particles you have in front of you, 1 of them is not water and the rest are water. And I think I just said that kind of weakly. It would be 1 part of the pollutant and 1 million parts of the water. The statement I made might make you think that it was 1 part water and then 999,999,000, etc. It's not. It's 1 per million. 1 to a million. Now, this graph is going down, so it has a negative slope, and you can even see that represented here. Remember, the number in front of the variable is your slope. So this right here is your slope. The 100, spoilers, is the Y-intercept, which we are not talking about yet. The rate is what goes with the variable. The rate is what we will do here, interpreting the slope. So before we actually go to the interpretation, what does this mean? This means that the concentration is going down over time. In other words, if this is a pollutant, maybe this is oil in a river or something like that, or nuclear waste, if you will, something even worse. It's going down over time because it's diffusing to the rest of the world or evaporating or seeping into the ground, something like that, whatever might be happening. Or maybe somebody is coming in and soaking it up. So here it starts out at 100 parts per million. And then it's just slowly going down. After 10 days, we're down to, I don't know, maybe like 94, 95, somewhere in that ballpark. And after another 10 days, it's down another to maybe, what's that look like, about 85, 86, I don't know. And then after 30 days, it looks like it's at about 80. So this is saying that eventually, in theory, it might go to 0. Arguably, it won't in the real world, but that's because linear models are not great approximators in the long term. All of this, not the point of the problem. We're just supposed to be interpreting the slope. So, sentence. Now, again, the part I asked you to write down is no longer on the screen, so hopefully you wrote it down, which is then bunny quotes output is changing by bunny quote slope, bunny quote y units, then per bunny quote x units. And they're not really quotes, they're sideways arrows, they're these things, which looks like the lesser and greater than. It's kind of a programming language thing, if you will. Anyways, so it goes and then the next thing was output. But you don't write this, you're supposed to write the units of the output. So the units of the output, I'm sorry, not the units of the output, that's later. We're supposed to write what the output is. The output is the concentration. The units come later. Like in the last one, we said the cost is blah, 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 blah. This is just a title. This is a name for the output. We're talking about the concentration of pollutants, and you could even be more specific and say the concentration of pollutants. So it's changing by, so I could say it's changing by, and then the number, the negative 0.8. I could do it this way. I could say it's changing by negative 0.8, or I could say is decreasing by, but then I don't write the sign. I keep wanting to say 0.08, and it's not. I don't care which way you do it. You can say it's changing by negative 0.8, or you can say it's decreasing by 0.08. But you have to have the sign correct, depending on the version you use. Now the rest of this was the y units per x units. That's the rest of this after the number. The y units, these are the parts per million, how we're measuring the concentration. The x units, this is the number of days, which is what's affecting the concentration. So it's 0.8 ppm per day. That's the interpretation. Or you could say the concentration is changing by negative 0.8 ppm per day. Either of those is 100% accurate. Doesn't matter, it'd be sound. Okay, so let's try this again. Houston population. And there's some weird stuff going on here. This is scientific notation, 5e plus 06 as kind of a reminder with scientific notation. The E tells you how far left or right you're moving the decimal. So what this says is you have your 5, there's no decimal written, so we assume it's behind the 5. And this plus 06, this E plus 06, this tells us to move the decimal right 1, 2, 3, 4, 5 times. 1, 2, 3, 4, 5 zeros. So that number is really 500,000. That's what that number really represents. If that had been a negative 0.6, the decimal would have gone left instead. And we will see an example with that. So again, this number right here, this is our slope. This is our rate. That would be the Y-intercept, which is kind of like the initial value. And as I said, in terms of applications, sometimes the initial value makes sense, sometimes it doesn't. We will start seeing a mixture of that in problems sooner than later. So growth in the Houston metro area, we're talking about the population growth. So over time, this years since 2000. This isn't years. It's not year 0, year 2, year 4. This is years since 2000. This right here is an extremely important distinction between just saying years. And I'm going to go ahead and spoil this. When you use just the word years, and we're talking about the year 2020 or 2015 or anything 2000 after 0, if we're trying to use linear models, they almost always kind of have poor interpretations. Using years since generally means we're looking at a smaller scale, which makes a line graph more accurate. So we're going to study this concept. Years versus years since, but not yet. Again, we're just getting used to these languages and ideas. Okay, interpret the slope. So once again, it goes the output. The output. I'll write it this time. The output, and then is changing by, then you write your slope, and you write the y units per and the x units. It's just a format you have to get used to. So the output, what are we talking about? We're talking about the population. Some people might say the growth in the Houston metro area. But growth, do you mean the growth in the size of the city in terms of land size, or do you mean people size? So I think it's a little important to be more specific here and say the Houston metro area population. If you were just a little more general and said the population or the Houston population, that's okay. Nobody's going to take points off for a group work or guided worksheet issue like that. And in my math lab, you can't even type these types of sentences, so that's not an issue. So this is the output, and then is changing by. Now you could say increasing since it's positive. I'm just going to say is changing by. And then we use the slope number, 1, 2, 3, 1, 3, 9. 1, 2, 3, 1, 3, 9. And then it goes the output units per x unit, the output units per input unit. What are the output units? We're talking about people. What are the input units? We're talking about not just years, years since 2000. So we're increasing by or changing by 123,139 people per year since 2000. So in other words, for every year since the year 2000, this city has been increasing by approximately 123,000 people. So in 2001, add another 123,000 people. In 2002, add another 123,000 people. In 2003, add another 123,000 people. And when you only look on a 10-year scale, that's a probably good approximator. If you actually looked at real world data, I bet you the real world data would something like, that was weird. Oh, I know why I'm on text. Draw. There we go. I bet the real world data would look something like this. I don't want to do that dot there. Maybe it's here, and then maybe it's like here, and then maybe it's here, and then maybe it's here, here, and here. So the red is representing real world data, actual measured data. The blue is used as a model to approximate the real world data. And I bet if we looked on this very small scale, these points would all be really close to the line. But if I bet if we looked at, the year from 0 to 2000, things are going to get a little weirder, and these dots aren't going to be that close. So that's what I mean by small scales versus large scales, lines being good or bad approximators. Again, we're going to be getting into that. I'm just trying to segue into it. All right. Clear, Annotate. Last one of these, the monthly interest. Monthly interest as a function of monthly balance. So we know that interest is a very simple equation when you look at it on one small time frame, the smallest time frame for the situation. In other words, if you're accruing interest monthly, you're looking at 1 month. If you're accruing interest daily, you're looking at 1 day. If you're accruing interest yearly, then you look at 1 year. And that's when we have just I, the interest, is the product of the balance and periodic rate. Sorry, this is being weird. It's just the periodic rate times your balance. That was one of the first equations I gave you back like 6 weeks ago. So they come up with this equation, y equals 0.05, excuse me, x minus 2e minus 11. So because that's an e minus 11, that says that decimal is going left 11 times. So you have your 2 with the decimal originally behind it, and then you move it left. I'm going to need to move that. Let's put it here, actually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. And that means there are 10 zeros that are going in there. I don't want to have to write every single one. So it goes 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then the 3. That's what this number is. It's being subtracted. That number is pretty much 0. This number is pretty much 0. If you actually wanted to spend that much money, it would be impossible. You can't spend any less than 1 penny, which would be right here. This is 1/10 of a penny. This would be 100th of a penny, 1,000th, 10,000th, 100,000th, 1,000,000th, 10 millionth, 100 millionth, 1 billionth of a penny. This is 3 billionths of a penny. It is literally impossible to pay 3 billionths of a penny as a person, which is why I do squiggly 0 here. And that's because in this equation, there is no number. There is no y-intercept, as we're going to get into. It's just a product of the rate and the balance. The balance is the x. Balance is the x. The periodic rate is this 0.05. This right here is your periodic rate. It's 0.5%, because 0.5% moving the decimal left twice is 0.005. So that's the periodic rate. Interest is just the periodic rate times the balance. There is no number. There is no number that gets added to this. But you might say, well, hold on, why is there a minus 0.003? Why is that there? This is because Excel is approximating data. Excel took these 1, 2, 3, 4, 5, 6, 7 points, and it did some crazy math on its own to come up with this equation. But when it does that, there can be these little subtle, tiny, microscopic errors. So what you'd have to do as a QR student is say, this is garbage. This isn't really supposed to be here. It's just y equals 0.005x. This isn't really necessary. Okay, on to the point of the problem. Interpret the slope of the equation in real-world terms. So back to our sentence, and I'm not going to write the sentence out this time. In the cookie cutter version, that is to say, I'm just going to write the answer. So it goes, the output. What is our output? It's monthly interest. So the monthly interest, and then you can say is changing by, or specifically you could say increasing since the slope is positive. You could use increasing instead of changing. And then you write the slope. So the 0.005 and then it goes the output units per input unit. The output units are these types of things on the left. What are these measured in? They're measured in dollars. So $0.005 per. And then what are the input measured in? Huh, that's weird. They're also measured in dollars. This is an interesting problem in QR sense because the input and the output data are the same type. Usually we're converting apples to oranges, something like that. We're going from minutes to dollars. But this is going from dollars to dollars. So it's based on a dollar amount to get a dollar amount. And this is a very important subject, studying interest. This is something we're going to have a high focus on in later chapters. So do I want to just say per dollar? That's kind of weak. It's changing by $0.005 per dollar. It also doesn't make sense because dollars per dollar, those units would cancel. So you're just saying it changes by 0.005. That doesn't make sense. So we have to be a little more specific in the dollar type of the input. We're talking about per dollar of balance in the account. Oh no, that's all right. Per dollar balance in the account. Or you could say per dollar of monthly balance. So the monthly interest is changing by $0.005 per dollar of monthly balance. In other words, for every dollar you have in the balance, you're going to gain $0.005 that month. All right, now that we have our sentence, I'll give you a second to write that out. And then I want to clear my screen and I want to look at these past couple of graphs because there's something important going on with this one in comparison to the last three. Okay. So let's just look at the last two since they're closer, but this one's the same. Look at the x-axis. Where does it start? It starts at 0. For the third one, look at the x-axis. Where does it start? It starts at 0, where you have this vertical line here, right here. This represents the y in the y-axis. So this line, the horizontal line, represents the x-axis when spelled correctly. And then this vertical line represents the y-axis. But it only represents the y-axis if that number is a 0. So in the concentration, here's our x-axis, here's our y-axis. We know it's the y-axis because here's a 0. Here we go, here's the first one. That's 0, so this represents the y-axis, the horizontal, the x-axis. But look at the last one. This number right here is not 0 on the x-axis. It's 16,200. This graph is not representing the whole picture. This graph is representing a very, 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 very small chunk of the picture. It's only representing the graph from 16,000, and it actually starts here technically at 16,400 to 18,000, and going from a height of 82 up to a height of 91. Notice the y-axis, it's not starting at 0 either. Let's redraw this graph. Here. Let's look at the much, much bigger picture. And in red, I will show you what we have. Actually, since they use blue, I'll use blue. So this blue, 1, 2, 3, 4, 5, 6, 7 points worth of data from 16,400 to 18,000. So let's have, here's our 18K. Let's just have this right here be about 16K. I'm not going to be able to draw this super accurately. And let's go from here to about here. And then this height right here would be about $82. And then this other height would be about $90, it looks like. If those are off, please forgive me. 90, not 98. this right here is the same graph as this. This little blue chunk of line is all of this right here, but now instead of starting this horizontal position at 16,200 and the vertical position at 81, now down here, this is $0. That looks like 50, it's 0. And then this would be $0. So in another color, let me do this in, say, black. This would be the rest of the graph, believe it or not. Please keep this straight as I can. Let me try one more time. There we go. That would be the entire picture. And then the rest of the numbers would be like 14K, 12K, 10K, 8, 6, 4, 2. And again, you'd have a bunch of other heights here, numbers, but they go down to 0, that's the point. So this graph does not look like it starts at the origin, but it actually does. If you were to trace this line back in the bigger picture all the way back to the zeros, this would actually go to the origin, because if you have $0 balance, that means you're going to get $0 in interest. That just makes sense based on the interest equation being a product of the rate and the balance. If your balance is 0, your interest is 0. But looking at this picture, you might not think that. You might think, oh, well, you know, since this is all the way up here at $82, if I have a 0 balance, maybe I'm getting 50 bucks in interest. You most certainly are not. So why have they done the graph like this? Why have they zoomed in, so to say? Maybe to confuse people, or maybe so they don't have to only be looking at this section because this is what's relevant, and over here is irrelevant because your loan, if this is a balance on a loan or something like that, maybe this is the range you were in for a couple of years, and you don't even need to see the future this much because you're like, oh, that's so far off, I don't even want to think about it. But either way, these graphs don't have to start at 0. You have to pay attention. It's only, this vertical line right here is only considered to be the y-axis if you're starting at 0, and that's going to be a question that comes up every now and then, because it has to do with the starting value. Actually, let me undo that. See, this starting value here, the starting value is the Y-intercept, as we've already kind of said. It's the initial height. And this was a 0, and this right here, this minus, is really minus 0. Whereas over here, you might think the starting value is $81, and it's not. That's not the starting value. The starting value is really 0, again, because if you look at the whole picture and trace it back. So pay attention to your graphs. If your graphs start at 0, then this is the y-intercept. So this value, let me just do it for these two. Because this graph starts at 0, this right here is the y-intercept. Because this graph starts at 0, this right here is the y-intercept. And we said y-intercepts can be interpreted as starting values. So that concentration's starting at 100. The Houston population is starting at, what's that, about 4.7 million roughly? Something like that. Now again, that's starting in the year 2000. The Houston population started at 0 or 5 or 2 or a very, very small amount of people way, way, way back in the day, but not necessarily in year 0. See, it doesn't really make sense to go back to year 0 for talking about Houston, because Houston's only been Houston for a couple hundred years. We don't want to go back 2,020 years to talk about a population of a place that didn't really exist. And I'm not saying there weren't people there. Maybe there were. There probably were. I'm not too familiar with population densities pre-America time. Honestly, I'm not too great with population densities currently in terms of just memorizing numbers or anything like that. But that's not my job. All right. So now let's get into this y-intercept stuff. So let's go back to our notes. Y-intercepts can be found by setting your input variable to 0. Now, very often it's x, but sometimes it's m for minutes, or d for number of days, or t for time, or days, or minutes, or hours, or whatever. So you can find a y-intercept when you have the equation by setting the x equal to 0. Or if you're looking at the graph, if you see 0 on it, it's the initial height at 0. So it's or the initial height if the graph starts at 0. Now this y, we called it y equals ax plus b previously, but we know that the letter that goes with the x is the slope. Historically, we denote the slope with the letter m, so that's why the much more common way to format this is called y equals mx plus b, and that's known as slope-intercept format. So y equals mx plus b is our slope-intercept format. We've already been referring to this format quite a bit. We are going to continue to refer to this format quite a bit. So again, the number that goes with the x is your slope. It is the rate of change, the fraction of differences between horizontal and vertical positions. The b value, this is the y-intercept. This is the initial height. This is the initial height of the graph. Now the cool thing is, if you know the slope and any coordinate, you can plug these three numbers in to find the value of the y-intercept. So if I say, all right, you've got a graph and we know its slope is 5 and it goes to the point 1, 12. You could find out what the b is by plugging them in. Let me show you what I mean by that. A line goes through the point 1, 12, slope of, did I say 3 or 4? Let's go with 4, doesn't matter. Find the equation of the line. Now, I didn't do any slope calculations previously. You will see 1 or 2 of those in the homework, but it's literally just subtracting, and dividing. I don't think there's anything crazy there, so I want to leave that open to y'all. And you have the view and example help me solve this to get you started in case you need that anyways. So a line goes to the point 1, 12 with a slope of 4. So, whoa, how did I get a third pen? I'm so confused. I'm sorry, this is weird. I've wanted to get another pen before and now all of a sudden there's another pen. How did that happen? I've got to watch the playback on this and see if I can find out what I did. That is crazy. I'm so, oh my Lord, there's just a button here that says add pen. I must have accidentally clicked that. Okay. All right. See, use your eyes, pay attention, and you discover things. Oh, this is fun. Okay, so when we talk about a coordinate pair like this, it always goes x, y. These are the x and y values. So that's what we'll plug into the x and the y in this format. This is an assumed format. Y equals mx plus b. We like having this solve for y because that way we can easily interpret the output. This 4, they said that's the slope, and I don't even have to say the slope. I could say with a rate of 4. If I say rate, that means slope. So this 4 right here is what will go here. So we're going to be plugging numbers into these 3 things, the y, the m, and the x. We don't plug anything in for this b. We end up solving for that. I don't want to leave this all circled and jumbled. So the x and the y are the 1 and the 12. So instead of writing y equals mx plus b, I'm going to write, instead of y, I write 12. Because the y coordinate's 12. Then instead of writing the letter m, I write what the slope is, which is 4. Then instead of writing the letter x, I write what the x-coordinate is, which is 1. We are plugging in one scenario. This point is one scenario. The m is always the same, but the points change. There are literally billions and trillions of points for every line. Plus b. We don't know what the b is. We're supposed to solve for b. Well, that's just 12 equals 4 plus b. So we're then going to subtract 4 on both sides. Oh, that's a wacky color. Let's not do that. I don't even know if I can call that a color. It's like spray paint. It's also a little thick. That's okay. I can edit that. So when you subtract 4 on both sides, 12 minus 4 is 8. 4 minus 4 is 0, and you're left with the b. So we went up here. So that tells us the value of b is equal to 8. Now the m is always the same. This is always 4 for this problem. It's not going to be 4 now and then 5 randomly. The b is always the same. The 4 and the 8, these are not going to change. So what we get is our equation, which I wrote the equation. Y equals, just write the mx plus b, but you're going to replace what the m is, which is 4, and what the b is, which is the 8. So the m, which is 4, then the x value, which is x, and then the b, sorry, which was 8. This is the equation of the line. This is the model for whatever this problem relates to. When you actually plug in a point, you are plugging in one scenario. That can enable you to check it or solve for a missing component. But when you actually want to write out the equation of a line, the x and the y have to be x and y. These have to be variables. They have to be allowed to change. But the slope for a problem doesn't change. The y-intercept for a problem doesn't change. Now what's cool is, with this y equals 4x plus 8, I can actually graph this if I wanted to. Because this is an 8, we know that the initial height, there's a point at a height of 8. That has to be a point. Because this is a plus 8, there's a point at a height of 8, a height of 8, not hate. Love, not hate. Because this is a plus 8, there's a height at positive 8. If this was a minus 8, it would be down here at negative 8. Now with a slope of 4, that says you're going to go right 1 and up 4 to find more points. So we can go right 1 and up 4. Because 4 as a ratio is 4 over 1. The denominator is how far you go right. The numerator is how far you go up or down, up in this case since it's positive. So that could give us a second point, and then we have our line that we can just connect and extend. So again, the constant value is the initial height, and that's if this is a 0 down here. This right here is 0 for my graph that I've drawn. How we can tell where the rest of the line goes is you can use the slope as a rate of change. You can change in the horizontal and change in the vertical in appropriate numbers. Whole numbers you can always write over 1. This is a very common issue with slopes, going from 4 to 4 over 1 or -7 to -7 over 1. So this is the more math side of things. Let's go back to the QR side of things. Sorry, was there something up here I wanted to say? Yeah, I want to point out just 1 or 2 things here before we get into the problem. So they talk about that, they go back to talking about the track phone problem where we had the $20 monthly fee, which raised the graph up 20 units. They literally demonstrated that with those vertical black arrows that I said we really don't like to draw, but it was a good visualization for that. And we also said that it didn't change the slope. The slope is all based on the number with the x. The y-intercept is all based on the number by itself. And then we characterize this as intercepts. If your input is time, then the x-coordinate is 0 can be thought of as the initial value or starting point. Unfortunately, if you have time series data where the inputs are years like 1990 or 1995, x equals 0 refers to 2,000 years ago. The year between BC and AD, if you will, also known as 0 CE. And I don't remember what CE stands for, so don't ask, don't tell. Don't ask, I don't know why I said don't tell. The Y-intercept will have no relevance today, because if you're talking about something having to do with the US didn't exist before, 1776, or if you just think about when it was colonized, the early 1500s. 1492, Columbus sailed the ocean blue, and we won't get into Columbus and how he was as a person, but anyways. This is the one time in this course where the correct answer may very well be this does not make sense. This is what I kept talking about, how short-term versus long-term scales. Very often when we think about something in a long-term scale, and I'm saying long-term, like 2,000 years, we're going to come up with models that don't make sense. We're going to come up with Y-intercepts that don't make sense. But if you look at years since, like we did in that one example, if you're only looking at 10 or 20 years, we can generally make the model make sense. But the point is, great care must be taken when you're interpreting Y-intercepts. Very often, we're doing a years since model instead of just a years model. So there is a major distinction in years versus years since. Okay. So that all being said, the worksheet asks you to interpret the Y-intercepts. So we're going to interpret our Y-intercepts. So we are no longer talking about the slope. The slope was this number right here, the 0.05. We're back to the cell phone plan. This was the M. This didn't say anything about talking about the slope, so we're just going to ignore it. We are talking about the Y-intercept. Interpret the Y-intercept. Remember, with Y equals mx plus b, and the plus could be minus, this right here is the Y-intercept. It tells you your initial height. So because this is a plus 20, that's our Y-intercept. And even on the graph, look at this right here. At a starting value of 0, the height is 20. That's our Y-intercept. But we need to make a sentence about this. And we don't give you a cookie cutter sentence for this one because I think it's a little easier to handle because you're not doing all this per and different types of units. You just need to say the output based on the input, and the input is always 0. The input is always 0 for a Y-intercept. So we're just going to say something like the output based on the input. The output's cost. So the cost is, what's that initial height? It's $20. Where's my dollar symbol? There we go. So the cost is $20 at 0 minutes talked. You could say something like that. Or you could say the cost is $20 when the minutes are 0. That's also fine. Again, it's a little more open-ended in how we can interpret it. They don't give you just an absolute cookie-cutter version of this. So there's no real drop-down menu idea for this in the homework. And who's to say on a final exam, I can't give you a couple of questions where you have to write out a sentence and turn it into me, but I usually don't. Again, the tests tend to be a little more just on the math side of things with some QR. These lectures and these guided activities are a lot more actual QR based. And when you're in the real world, that's probably what you're going to be dealing with, is a more of a QR idea than just doing math with equations. So the cost is $20 when the minutes are zeros, when the minutes are 0. This is like an initial cost or fixed fee. That was the $20 we pay no matter how many minutes we talk on the phone. We talk 0 minutes, we're paying that 20. We talk 1,000,000 minutes, we're going to pay for those 1,000,000 minutes, but we're still going to pay the 20. Give you a second to write that because I got to clear my screen. So we can move on. Okay, clear. Let's go back to the pollutants. So again, just interpreting the y-intercept. We already interpreted the slope. It's literally the same thing because it's literally the same number. So we are focusing on the plus 100. That's our y-intercept. The graph starts at 0, which means this point should also be the y-intercept. So our interpretation of this initial or fixed value is that the concentration, the thing we're talking about, the output, is 100 parts per million at day 0. This is probably the day of the spill. If we're talking about day 0, this is probably when the spill happened. It could also be when we started measuring it, but the fact that it was exactly 100 seems interesting. And it doesn't have to spill at exactly 100. So that's why I said this is probably the day of the spill. You could also say, or the day of initial measurement. But I'd hope that the second some people spill stuff, they're already taking measurements. I can't guarantee that. Maybe Exxon Valdez has the spill and hides it for a couple days or something like that. I'm not saying that's what happened or what will happen. So that's the initial concentration of pollutants. And because they're slowly seeping into the ground or diffusing or dispersing or whatever you want to say, they're slowly dropping over time. Now, do they drop in a linear fashion on the long-term scale? No, but if you're only looking at a few days, they probably can be considered to be dropping in a linear fashion. It's kind of like when we look at the population of people who've got a certain virus. When you only look at a few days at a time, it looks like a line, but if you actually pull back and look at the whole picture, it's a curve, it bends, it changes significantly at times. Okay, so it's clear. Let's go to the next one. Let's go back to that Houston population. Now, you're seeing two equations this time. And they say to please interpret both numbers. So one of these is, ow, sorry, I just popped my shoulder. One of these is what Excel is displaying, and one of these is the actual number that it's holding. So let me see if I can scroll this down. I'm not going to be able to keep the title, but it was Houston population. That's what that said. So this top one with the 5e plus 06, this is the displayed equation in Excel. But this right here with the more specific number, 4715407, this is the actual value Excel holds. When they display equations, they don't like going past a couple shown digits of accuracy. So they don't want to have to write this. So what they do is they display this 5e plus 06 to say, hey, it's a big number. But when it's doing its calculations, or if you actually go in and double click it and look further, this is the number that's really there. So this 5e06, remember if you take the decimal and move it right 6 times, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. I think I did one too many. Yeah, I did. That's what happens when you go too quick, and it's going to erase all of them. That's okay. Draw, please. Thank you. 1, 2, 3, 4, 5, 6. So that's really 5 million. So Excel is saying, all right, this number is about 5 million, but in reality, when we do our calculations, we'll use the real number of 4.7 million and some change. So again, these are the numbers that we're interpreting. Those are the Y-intercepts. So what are we going to say? Well, The output, the Houston metro population, was, let's do the real value first, 4,715,407 people. Now, this graph starts at 0. I can't circle it or it'll mess my text up. But this graph does start at 0. Look at this, it starts at 0, it goes all the way back to 0. And this value right here, this height should be the population at year 0, but it's not really year 0, it's years since 2000. 0 years since 2000 is the year, hopefully no surprise, 2000. We're not saying that the Houston population was 4.7 million in the year 0. It definitely was not that. But we could say it was 4.7 million some change in the year 2000. That's why we're using this particular type of model. We will see this problem later where we do it as just years and things are going to change significantly. So what happened with the other one? Excel rounded this to the 5 million in scientific notation. Conserve space. So again, because this was the year 0, that's the Y-intercept. Ten seconds. All right. Last one like this, monthly interest, and they have the sentence down here, but there's space. I can do it up here. They say, interpret the Y-intercept in real world terms. Be sure to convert the scientific notation to a number that's more understandable. So we already did that earlier. We said that this number right here, this is our Y-intercept. But graphically, we cannot visualize the Y-intercept because this doesn't go to 0. So graphically, we don't see the Y-intercept. And that's because this number is not 0. So you have to be careful with your interpretation. We can still interpret based on the equation, but not on the graph. So this minus that number was really 0.000056788910 and then a 2. That's what this number is. Not in scientific notation, which we said was pretty much just 0. Because when you think about in terms of real world money, you can't spend 0.00002. It's nothing. This sounds like one of those schemes where one of those movie schemes where you write some code to round off the fraction of a penny and add it to your account so that you're a billionaire in 10 seconds, and then you run from everything. You know the movies I'm talking about. There's half a dozen of them around, especially from the early 2000s, late 90s. Okay, so the actual interpretation of the Y-intercept. So that number, what are we talking about? The output is talking about monthly interest. So the monthly interest is negative 0.12345678910 and that's in dollars. When the monthly balance, that's the input, 0. This is a little weird though. This very small decimal value was found due to Excel approximating the the equation based on data points. In reality, it's so small that it should just be 0. So a better way to say this is really, much more accurately, the monthly interest, I'm missing an H. Monthly interest is $0 when the monthly balance is $0. That's the real, what happens in the real world. If you have $0 in a bank account, you're getting $0 in interest. You're not going to get a negative. First of all, you don't get negative interest if you have money in a savings account. Interest is always a positive value. And you might say, well, what about when I have a loan? Well, then interest is just positive relative to the bank or the person you're borrowing from, whatever it might be. So again, this is due to round off error, truncation error. There's this thing called the sum of least squares, all this regression stuff that we don't get into any of the math. Thankfully for y'all, it would take me about, I don't know, 3-4 weeks to teach you that math, and then one problem takes an hour to do half the time. It's not fun. You don't want to do it. Fortunately, Excel will do all that work for us, as it has done for this. So again, what Excel does is you have these points in a chart in Excel, you highlight them, you go to do a scatter plot, and then when you build the equation, it displays this for you. It does all that math. Okay. I know I wrote a lot, so I'm giving you some time to catch up. And if you're watching this on YouTube after the fact, you don't really need that time to catch up the pause button, but I do have some students that watch live. So we're treating it like a real class. Oh, and that reminds me, I need to make an announcement at the end of class about something having to do with the live classes. Save it to the end. Okay. If you didn't catch everything, like I said, just go back to the YouTube recording. Let's go annotate. That should be it for that one. Here's your Excel preview for population. This is another one we'll get to. And this kind of demonstrates the idea of looking at the years since model, and then looking at a just overall year model. So here is some data points, the blue dots, thicker blue dots. And then Excel goes in and does its magic, and it makes this line as an approximation for us. And I'm going to show you how to do that in just a few minutes. Maybe not a few minutes, but soon. And then Excel comes up with this equation as well. So it does a lot of things for us. It gives us a picture of an approximation, and then it gives us the equation. And this is a linear approximation, and it looks pretty good. These points are all really, really close. And you can see this one looks like it's a teeny bit lower. This one looks like it's a teeny bit higher. This one might be a teeny bit higher. But this is really, really good in terms of accuracy, because we're only looking at like 60 years worth of the model. But look at this one up here when we try to do a linear approximation of this. The population, when we look at hundreds of years, these dots do not follow a line anymore. When we only look at 50 or 60 years, they look like they follow a line. But when we look at a couple hundred years, there's bending involved. This is a curve, which means when Excel is used to approximate this with a line, there's no way it can be 100% accurate. See, it's pretty good right here. They're pretty accurate. It's pretty good right here, but before, it's kind of crappy. After, it gets even crappier. In the middle, it's okay, but it's not great. So when you look at longer time frames, linear models tend to fall apart. And this is going to get even worse as you move on. If you go into the year, say, 2200, this model says that, oh, okay, I just predicted it keeps changing constantly. But in reality, it's probably going to keep exploding like that and get further and further and further. This error gets worse over time. Now, does this explosion keep happening? In fact, no. Eventually, it has to taper out due to population dynamics, due to the fact that there is a maximum population of this planet. We don't know what it is, but it's there somewhere. So this is a really fascinating Excel assignment. As I said, you will most likely be assigned. And we will kind of get more into this idea as well outside of the Excel assignment. How does Excel actually take these dots and then make a line out of it? How does Excel actually display this equation? Let me go off annotate. This last little bit honestly won't come into play until chapter 8. So it's there, but don't sweat it too much. How to add a trend line and the equation or R squared of a model. R squared is very, very important. It tells you how accurate your model is. We'll get into that interpretation in chapter 8 though. That's why I said it's important later. So you highlight your data and labels, then you go to insert scatter plot, it looks like dots. You add your chart, go to add chart element, trend line, linear, and then to the R, for the R squared part, that's what this is, add chart element, trend line, more options, and then R squared, and display equation. So let's focus on this part for now. Highlight data and labels, insert scatter plot. So I'm just gonna make, really quickly in Excel, oops. I'm just gonna put some random points up here. Let's go X, Y. Let's say we have X values of 0, 1, 2, oops, not 23, 2, 3, 4, 5, and 6. And let's say the Y values are 2, 5, 8, 12, 17, 20, and 25. So these were just, maybe the X is time and the Y value is a number of items to produce. So 0 minutes in, you made 2 items, 1 minute in, you made 5 items total, 2 minutes in, you made 8 items total, you're picking up speed a little, 3 minutes in, you made 12, 4, you made 17, 5, you made 20, at 6, you made 25. So you're speeding up, you're slowing down, you're not working at the exact same pace every single second, because maybe 1 minute you're talking to your buddy, 1 minute you're a little tired, whatever. All right, so what does it say? Highlight data and labels, then go to highlight data and labels, then insert scatter plot. So let's highlight our data and labels. Then we go to, oh, that's going to be annoying, insert, and then my scatter plot is right here. Looks like a bunch of dots. Insert, scatter, or bubble chart. Now, sometimes in your Excel homework, you might have to go to recommended charts. Remember, that's always a possibility. And then they give you some options where they're connected and shown as bubbles. It's generally the top left one that we want. And it shows you the output label. It doesn't show you the input label, just the output. I could go in and add data labels for these as you've been instructed previously. So here's the dots. But then we want Excel to build our trend line, the graph that is approximating it. Sometimes the approximations are 100% accurate, sometimes they're a little off. So go to add chart elements, and you might not be able to see it. I'm going to maximize this so it looks normal for everybody. Add chart element, trend line, linear. So when you're under design, if you're not under design, it's not there. See, it's not there. I got to make sure it's under design. If I had the graph highlighted, it should still be there. Add chart element, trend line, linear. And before I hit my button, look what happens if I just highlight any of the others. Moving average. You talk about moving average a lot with this virus going on. That's 7-day moving average. Because you might have giant bursts one day and then not another day because maybe they're not collecting data on a Sunday, something like that. So Monday, you might have a lot more influx. But exponential, what does that mean? Let's wait a chapter. We'll talk about that. It's very important for long-term models, though. Linear. And look at this. It makes a line. And these points aren't exact. If this data was perfectly modeled, then they would be exact. And that can happen too. This one's just a little off here, a little, teeny bit off here, teeny bit off there, but it's pretty good. So that's how we get the graph, this linear approximation using least squares regression. That's the fancy name for it. We don't do any of the math. Excel does all the math for us. Thank you, Excel. All right, the next thing we wanted to do was to display the equation, you go to add chart element, trend line, more options, and then display equation. So back to add chart element, back to trend line. We'll go to the very bottom, more options, and a little side menu opens up. Now under that, you can go and change this to a logarithmic growth, and I don't have enough values based on that because of the 0, unfortunately. Let me undo. So don't click that one ever in this course. Polynomial, you can see it looks a little different. Exponential looks a little different. But we were just doing linear, so let's leave that on linear. We're looking down here. These are the two important buttons. Until we get to chapter 8, the last one's not really seen, but I'll go ahead and tell you how to get it. So display equation, and it's a little small. If you highlight it, you can move it, and you can grab one of the arrows sometimes. I don't know why it's not letting me do it. You're supposed to be able to make that bigger. That's okay. I'm not going to worry about that for now. But you can see it's 3.8571x plus 1.1429. Then back to add chart element, trend line, more options. Now, if I hadn't clicked that, this would have still been up, and I can hit display the r squared. So this r squared, the fact that that's 0.99 is really good. R squared is typically between 0 and 1. 0 is bad, 1 is good. We'll get into that later. For now, all we're really worried about is how to get the picture and how to get the equation, which we're all under add chart element. Trend line. To get the line, you just hit linear. To get the equation after the fact, you go to more trend line options. This menu should open up. If it doesn't, if another menu is already open, you might have to close it and then try again. And then you hit your display equation on chart. And you can see the little check boxes. When you uncheck them, they go away and add. Because I moved it, it now doesn't think it's there anymore, and I can put it again. Don't worry about that. It's just silly. Let's do one more of these, just for good practice. X not xj, y. Let's go 0, 1, 2, 3, 4, 5, 6. Let's have this be a really, really terrible one. Let's go with 50, then 2, then 38, then -5, 17, 40, and 41. Highlight the data. Insert. Scatter chart. Look at that. These points are all over the place. So there is definitely not a line that's going to model them really well. Add chart element, trend line, linear. That line looks like hot trash, and oh, that doesn't really model that one or that one or that one or that one or that one. This is really bad. Check this out. Add chart element, trend line, more trend line options. Let's display the equation. So that's the equation that approximated. It looks like it says equals x plus 23 and some change, so that's a 1x. If I display the r squared, it's 0.01. That means it's terrible. These data points are not very accurate. Let's do another one of these. 0, 1, 2, 3, 4, 5, 6. And let's have y values be 10, 12, 14, 16, 18, 20, 22. Highlight the data and the labels. Insert. Scatter chart. That looks like a pretty good line. Add chart element, trend line, linear. Now see, I already had this submenu open. No, I didn't. I'm sorry. I made the line. Ignore me. Trying to do too many things at once. Look how accurate that is. See, this one was really good, but a couple were a teeny bit off. This one is, it looks perfect to me. Add chart element, trend line, more options. There we go. Now that time, it didn't pull up the right menu, so we close it. Add chart element, trend line, more options. Display equation, display 2x plus 10. Display r squared, 1, that's perfect. That means the data matches the model perfectly. When we talk about people, it rarely happens. When we talk about long-term timescales of things, it rarely happens, but it can. When we talk about money, if we have specific types of accounts where interest rates are fixed, these models are perfect. Now, if they vary from day to day, they're not. So this is going to be an important idea moving forward. You're going to have Excel homework where you have to do things like this. So please understand how to, and that's why I did it several times. Again, the r squared, not really an issue yet, but it will be by chapter 8. All right. Are we on time? A lot of the stuff in 5.3 is just kind of retreading 5.2. So I am going to spend about 10-ish minutes talking about this. I don't want to cut too much time from class. I know I gave us a few minutes out last time, but I can't keep doing that, unfortunately. So 5.3, linear equations, which is everything we've been talking about in 5.1 and 5.2. Everything in 5.1 was a linear equation. Everything in 5.2 was a linear equation. Note, the y-intercept of a proportional relationship. Now remember, if something's proportional, that means if one thing is 0, the other thing is 0. The y-intercept of a proportional relationship is 0 and generally not written. That's when there is no fixed or initial amount. When you start at the origin, this is a proportional relationship. If this is 0 and this is 0, that point starts at 0. So the y-intercept is 0. And who's going to write 0 here? Who's going to write a 0 for that? Mx plus 0? No, just write the mx. There's no b to be written. Versus a non-proportional relationship. This is when we don't start at the origin. It means there is a fixed or initial amount. So this would be not proportional. It still shares ideas and concepts with proportions, but it's more about the change. As you double the x value, the y value would double relative to itself. So if you double the change in the x, you double the change in the y. But again, you can't just say if one doubles, the other doubles. So the y-intercept, this height would have to be a b, so it's y equals mx plus b. So the blue version, there is a fixed or initial amount. You're paying that $20 fee. You have that 100 parts per million of concentration initially. The red one has no initial or fixed amount. So you're just paying per minute. There is no fee, or there is no initial concentration of garbage in your lake or river or water or whatever. Remember, slope-intercept form is y equals mx plus b. I've now said this like 5 or 6 times today. And remember, if you know the slope and any coordinate, you can plug these 3 numbers in to find the b, which is the y-intercept. We showed you an example of that last time. This is very much just retreading the same stuff as before. When we get into the guided worksheets, we'll kind of start opening more interpretations again. The larger the value of m, the steeper the line. M can also be negative. Oops. No, sir. Yes, sir. There we go. So let's say this was our line. Let's say this line has a slope of, and I'm going to write the positive for clarity. Let's say this has a slope of +1. This line is steeper, and maybe its slope is +3 or +2. Let's say this line right here has a slope of -1. This line would be steeper, so it would have maybe a slope of, say, -2 or -3. The larger the value, the steeper the line. Imagine you trying to walk across these lines from left to right. The larger the slope, the harder it would be to walk across that as a floor. It would also be more difficult to walk across it as a -3 versus a -1. That's more because you're fighting tumbling versus the force of gravity. If you're given an equation that's not in y = mx + b format, just solve for y. This is a very, very common issue to put it in slope-intercept form. So let's say your equation is 2x plus 5y = 10. Let's say I give you this as your equation or your model. I mean, that's fine, but we really like these to be in y =. Excel cannot handle it in this format. Excel needs this to be in y =, so we need this to be in y =. So we just solve this for y. What you do is you subtract 2x on both sides first, which would give us 5y = 10 minus 2x. And then you would divide all terms by 5. Now with division, you have to divide everything on the left and everything on the right. It works a little different than subtraction. So you divide the 5y by 5, the 10 by 5, and the 2x by 5. Sorry, I was saying 2 at the same time. 5. And what that would give us is the 5's cancel here to get y =. The 10 divided by the 5 is a 2, and then that's a minus 2x over 5. If you don't like the fact that the constant's first and the variable second, you can put it in the more appropriate form, minus 2x over 5 plus 2. Both of these are accurate. Both of these are correct. But this is more like in the mx plus b format. Now you might say, well, why did the sign swap? Because the negative goes with the 2/5 x term, the positive goes with the 2. So when I move the 2 to being second, the plus goes with it. And then the last little bit of these notes, 2 words for association. Accumulation means positive slope, depreciation means negative slope. To accumulate something means to get more of it. To depreciate means to lose. So like our cars, unless you're driving a 1969 Shelby Mustang GT 500 KR with all sorts of fancy car parts and stuff, that car might appreciate over time. But if you're driving a 2008 Civic, it's depreciating over time. It's losing value because mechanical parts rust and break and erode and become just, crappier over time, so to say. So cars depreciate, means they lose value. So if you were to model the value of your car versus time, it would have a negative slope. Accumulation means to gain, to accumulate things. So maybe you are saving money every year. Maybe you're accumulating $1,000 every, let's just say $1,000 every year. So if you modeled your savings account, you would see that it has a positive slope because you're gaining $1,000 every year. So your rate of change is $1,000 per 1 year. This last bit is just a reminder. This is literally the same thing that we saw before. Slope is rise over run. The denominator tells you how far you go right. The numerator tells you how far up or down you go based on the sign. That should be it for that section. So again, let's say our slope was 5/2. The denominator tells you how far to go right. The numerator tells you how far to go up. And that's from any point. That's not just resetting to the origin. So if you have a point here, I'm not saying this is the origin. I'm saying this is a point somewhere randomly. You would go right 2 and up 5 to make another point. And then from there, you could go right 2 and up 5 to make a third, right 2 up 5 to make a fourth point. You can connect them and make your line in that manner. If your slope was, say, -5/2, you'd be going right 2 and down 5 instead, but remember there is no left. So if here's our initial point, you'd go right 2 and down 5. And you can see you end up with a negative slope because it's going right and down. So we'll get more into that next time. We'll get into the guided activities. We're really going to finally get into comparing and seeing the difference of a years since model versus a years model. We're going to get some uglier numbers and find slopes. They're not just going to be nice, pretty 2s and 5s and 7s anymore. All right, so let's pull up, not this, this, our daily notes, just as a reminder. Project's due on the 21st. Next Excel is due on the 16th. You're going to have, I think, 2 more Excel assignments after this one. I think there's going to be 2 more. So one due on like the 23rd, and then probably one due the last day of class, which is probably the 30th, I guess. Does that sound wrong? That doesn't sound right. I think we're already out of class at that point. I need to check the schedule. But we will still have 2 more Excels after that one. 5.2, we finished. We're also going to have that due on the 13th. So that's a week from today. That should be enough time for you to have finished your exam and to catch up on the work. Don't just wait till the last day to do the exam. Start it sooner because you got 2 attempts. I'm giving you a lot of awesome opportunity here to make good grades. Remember that the midterm is worth 20% of your grade. This is one of the 2 biggest chunks of your grades. Most of our work's 15%, homework, Excel, quizzes. Then we have the 5% for the project, 10% for participation, which I think everybody's doing pretty good with participation. I think most people should have 100s on that, or 90s, A's at least. All the details about the midterm, which you've seen several times. Make sure you are prepared for that. Make sure it is your own work. What did I want to say next? Oh, okay. Hold on, I'm pulling up my calendar. Thursday the 16th. That class will be pre-recorded. Most likely Wednesday the 15th. I have an important family matter to attend that, yeah, I mean, I'm just going to say that. I have something to attend, so I cannot teach my classes on Thursday. However, given this opportunity, I can go ahead and record the lecture on Wednesday, go ahead and upload it, and then when you come in on Thursday, instead of showing up for class at 8:30, you can just watch the video on YouTube, or if you want to watch it Wednesday, you can. And as I've said, I only have, honestly, I think 3 of you who even attend the live lectures. Most of you are watching it after the fact, if you're watching at all, which I hope you are. Otherwise, how do you know when things are coming up, right? But anyways, the point being, this means I don't have to cancel class as long as I have this pre-recorded, which I absolutely will. So that date's class will run normal for the most part, except if you want to watch it from 8:30 to 10:30 a.m., just go to the YouTube link that'll be provided. And as I said, I'll actually upload it early. So whenever I have these recorded, within 30 minutes, they'll be in Canvas, the link to YouTube, and you could go ahead and do it then if you wanted. And I'm sure most of you are going to wait till Thursday, but maybe 1 or 2 of you want to go ahead and get it done. It'll be just like all of this. I'll have stuff typed up ahead of time. Nothing will change. You just won't be able to ask me a question in chat. If you have a question, shoot me an email. So again, sorry that I have to do that, but fortunately, I think this isn't going to really have a major effect on anyone. So that's kind of awesome. I like that issue. All right, so we'll call it a day there. Midterm is live midnight, 12:01 a.m. You have 3 full days. You got Wednesday, Thursday, Friday. 2 hours each attempt, 2 attempts. I take the best attempt. Keep studying, keep working, check out your reviews, get to those Excels. If you get that midterm done and you got an A on it after your first attempt, go ahead and get back to work on the Excels. Quizzes are going to fire up again starting next class. Excels are back in the pipeline. My math lab and my math lab homework never ended. All right, so we'll call it a day. Have a good one. If you have any questions, email me, and I'll see you on Thursday.